Morning. Last week we took a look at our basic trig functions. That's sine of theta, or an angle, is equal to the opposite over hypotenuse. Cosine of an angle is adjacent over hypotenuse, and tangent of an angle is opposite over adjacent. Now these are applied to the angles of right triangles, and they let you figure out some of these other sides. And that's kind of what we looked at in that worksheet. Was I might have given you a side and an angle of a right triangle, and you had to find the other one, the other side, that is. But the question kind of becomes, well, what if I gave you two sides, but I didn't give you the angles at all? Could we go backwards with this? And the answer is yes, we can. And we kind of do it in the same way, at least thought process-wise, as how we might undo some of our operations in math. For example, if I gave you an equation and it had like a +7 on one side of it, and I wanted to move that or get rid of it, then we would subtract 7 from both sides. Multiplication we undo by dividing, division we undo by multiplying. In the Pythagorean theorem, how did we undo the squares? We took the square root. Whenever we were rationalizing a denominator that had a square root, how did we undo that? We squared it. We multiplied it by itself. So all of these functions, they typically have some way to undo themselves, and these functions here are, well, the same. They have a way that we can undo them. And when we undo them, we end up getting back the angle that's inside here. We kind of just get that out. So here's kind of what it looks like. It's called the inverse. So we have the inverse sine. And if I apply the inverse sine to, say, the sine of theta, then I apply this to both sides. Let me actually really write this out. So here's our equation. Sine theta equals opposite over hypotenuse. I can apply the inverse sine to both sides. So I can take the sine inverse of the sine of theta. And I can then also do that to the other side. Take the inverse sine of the opposite over the hypotenuse. And this is no different than, say, like squaring both sides of a problem, or taking the square root of both sides of a problem, or multiplying and dividing by both sides of a problem, in that we have to do it to the entire side. Now, taking the inverse sine of the sine, they cancel out. Just like when you take 5 and you divide it by 5, it went to 1. It's a little bit weird how it's all written and how it comes out. It's not completely perfect, but for the sake of our geometry class here, it undoes itself, and we get left with just this angle. So the inverse sine of the sine leaves us with the angle. So now theta is equal to the inverse sine of the opposite over hypotenuse. And we could do that with all of these, with their respective inverses. So I could take the inverse cosine up here, and I would get the cosine inverse of the adjacent over hypotenuse. That's what theta would be. Same for the tangent. Theta would be equal to the tangent inverse of opposite over adjacent. I'll write it out here just in case. Theta equals tangent inverse of opposite over adjacent. So let's take this and apply it to some examples that you're going to see. We're still going to be working with a right triangle for now. You'll see eventually here we'll start working with a not right triangle, and these things will still come up every once in a while. Oh, and by the way, some calculators, instead of having the sine to the -1 or cosine to the -1 like that, they might have arc in front. So arc sine of sine theta equals opposite over adjacent. Arc sine opposite over adjacent. And then the arc sine and sine cancel out. It's just another way of saying the inverse sine. Okay, so first example, and I'm just going to take these again straight from the assignment that I'm giving you. So the first one, we've got a right triangle that is 5 millimeters on the hypotenuse and 1.4 millimeters on a leg. So here is 5 millimeters and 1.4 millimeters. And the problem is requesting this angle down here. Now, you're going to need your calculator, and again, make sure you're in degrees for these. I want to stay in degrees with you guys as much as possible while we're doing this whole at-home learning thing. We're just going to stick to degrees. So what we want to do is we want to look at the angle that we want, that's this one, and we want to keep thinking the same kind of thing that we did in the last assignment that I gave you guys. We need to identify the sides that I gave you based on this reference angle. So this side right here, the 5 millimeter one, that one's obvious. It's because it's opposite the 90-degree angle. This is my hypotenuse. And the 1.4 millimeters looks like it's opposite the angle that I'm looking for. So this is my opposite side then. Which one of my trig functions used opposite and hypotenuse? Well, it was the sine. So just to spell it all out, the sine of whatever this angle is, let's call it theta, the sine of theta is equal to the opposite, which is 1.4, divided by the hypotenuse, which was 5. Oh, no! But I don't want just the theta here. I don't want sine of theta here. I want just theta here. So I have to undo the sine by taking the inverse sine of both sides. And now the inverse sine and sine goes away, and I'm left with theta is equal to sine inverse of 1.4 over 5. And as you get better and better at these and recognizing them, that step just kind of becomes second nature, and you'll just jump straight to this final result here. You'll recognize opposite and hypotenuse, that's sine. You want the angle out of it, so you want the inverse sine of that ratio instead of the sine of the angle. So if you type this in on your calculator, we get inverse sine of 1.4 divided by 5 to be 16.26. So theta equals 16.26 degrees for number 1. You could use the same thing to figure out your third side if you wanted, or alternatively, you could just know that every triangle has to add up to 180 degrees, and you can figure out that last angle. Right? So if this is 16.26, then up here you would have to have, what, like a 73.74, something like that. And you should get that as well if you were to do, say for up here, like the cosine inverse, because this would be adjacent then for this angle and hypotenuse there. All right, let's move on to another one. Okay, so looks like the majority of these, at least the first ones, all include the hypotenuse, which is fine. Let's do number 11, 8 centimeters and 5.2 centimeters. 8 centimeters, 5.2 centimeters. And we want this angle right here. So in reference to this angle, we have our hypotenuse. I know that because it's opposite the 90 degrees. And we have the adjacent. Adjacent and hypotenuse, that's cosine. We can jump straight to the end maybe if you're starting to catch on to this. Adjacent over hypotenuse. I want to do the cosine inverse to get the theta out of this. So theta is going to be equal to the cosine inverse of that ratio. And if we do this, 5.2 divided by 8, I'm coming up with 49.46 degrees. Super, super fun time. Let's do one tangent problem just to make sure we see it. And then we will solve one full triangle, every little bit. So for a tangent problem, let's take a look at number 14, because why not? 9.6 and 2. Is that right? Yeah, that's very, very not drawn to scale. Let's try to make it a little bit more drawn to scale than it is. 9.6 and 2 meters, and I think we want this angle down here. No, we didn't, but that's okay. All right, so for this angle, I've got opposite, and I've got adjacent. Opposite and adjacent means we want tangent. So opposite over adjacent is 9.6 over 2. I can do the tangent inverse to that to give me the angle, theta. So if we do the inverse tangent to 9.6 divided by 2, we're going to get 78.23 degrees. One thing that I do want to show you guys to make sure, now that I'm looking at it here, because I know somebody's going to mess it up, on your calculator, make sure that you have, and it's not going to focus, I'm sure, make sure that you have that ending set of parentheses here. Or write the whole thing as a fraction. On your Casio calculators, you can actually put in a fraction. If you can't put in the fraction, end those parentheses. Put this whole thing in parentheses. 9.6 divided by 2, close parentheses. Otherwise, your calculator is just going to see you want the tangent inverse of 9.6, and then whatever you got, you want to divide that by 2. We don't want that. We want the ratio to be the thing in the tangent inverse, along with all the other inverses as well. So make sure you close those parentheses. This is a good enough example here. Let's solve the rest of this problem. Let's figure out every other bit of this, and we're going to do it using trig only, not the other stuff, because I could figure out this other angle here, knowing that every single angle in a triangle has to add up to 180, so I could just do addition to figure that out if I wanted at this point. I'm not going to. I'm going to use trig to figure it out. And I could figure out the hypotenuse of this triangle by using the Pythagorean theorem, but again, I'm not going to. I want to use trig, because that's kind of the whole lesson that we're in. So we might as well see how we can use it. So let's move to this angle up here. We'll call this one maybe x. Why not? For angle x, opposite is the 2 meters. So I'm going to get rid of this adjacent label now. This is my opposite now for this angle up top, and this one is my adjacent. Now, x will be equal to the tangent inverse, because I'm solving for the angle, it's going to be the inverse of 2 over 9.6. So we do the tangent inverse of 2 divided by 9.6, and we get 11.77. X equals 11.77 degrees. And if you look, yeah, it looks like it does actually complete that 90 degrees right here that we would need to make the full 180 given the other 90-degree angle. So that's good. Now we know both of our angles. We need to know this last side. It's a hypotenuse, so I want to use either the sine or cosine of an angle to figure that out. You're free to pick whichever angle you want here. Don't pick the 90 degrees one though. I'm going to go ahead and just pick this one down here. because it's the one that we used at the very beginning. So we know that that angle is 78.23, which means I could do something like the cosine of 78.23. That's what this angle is. This is just like the last assignment at this point. So the cosine of that angle should be equal to, for cosine, it's adjacent over hypotenuse. So the adjacent is the 2, and the hypotenuse is, we'll call it y. It's the thing I don't know yet. Solving for y, I get y is equal to 2 over cosine 78.23. And if you type that into your calculator, 2 divided by cosine 78.23, I'm coming up with 9.80. And then some other numbers, but 9.80. That's what y is. So, we can take any two pieces of a triangle that I give you, as long as it's a right triangle, and we could solve for every single other piece of it using a combination of trig functions or inverse trig functions. Those would be your theta equals sine inverse, opposite over hypotenuse, theta equals cosine inverse of adjacent over hypotenuse, or theta equals tangent inverse of opposite over adjacent. So we can use any combination of these, and we can completely solve a triangle. But sometimes it might be a little bit easier once you get that second angle. To get the third angle, remember they've got to add up to 180 degrees to be a triangle. And likewise, when you get two of the sides, you can use the Pythagorean theorem because this is a right triangle. Sometimes those things make it a little bit easier, but you can certainly use trig, these 6 things, to get the job completely done from start to finish. Next thing that we're going to be doing is we're going to be completely solving some triangles, and then we're going to see how this trig stuff can be applied to triangles that don't have one of these. It gets a little bit ugly, but we'll make it. Couple weeks left, guys. We're almost there.